All right. Yes. Can you hear me, students? Are you back?
Yes, sir.
Yes. Thank you so much. Actually, it is only now I can see 26 students, and you are really engaged in this lecture. That's why you joined immediately. Thank you so much for your attention. Thank you so much. Okay. So yeah. So you understood my problem, right? So can we able to get a embryonic stem cells without using embryos? Is it possible? That is the idea of our this Shinya Anamaka. He is one of the best scientist students. He got Nobel Prize for his creative approach of getting stem cells. You know what he did is beautiful. I will tell you. Listen, uh, can we able to convert an adult cell into a stem cell? That is his question. I know that a stem cell, a mesenchymal stem cell, for example, a mesenchymal stem cell converted into a skin cell, a heart cell, and a pancreatic cell. A pancreatic cell. Can I able to reprogram the cell? Can I do reverse engineering? Can an adult cell convert into a stem cell? Is it possible? Can an adult cell converted into a stem cell? That is his idea. And his approach is very good. He said, okay, to convert into skin cell, this stem cell used some COX cytokine. Maybe COX is a cytokine. These three cytokines used by this stem cell to convert into a skin cell. Right? Then, shall I revert? That means some of the genes are activated and some genes are deactivated. Okay, some genes are deactivated. That's why it became an adult. Some genes has been deactivated. That's why it's become an adult. Now, can I reactivate deactivated genes? Can I reactivate the genes that are shut down in the adult cell? Can I able to reactivate the genes present in an adult gene? If I reactivate those genes, my adult cell can be converted into back pathway. It will be converted back into a stem cell. It will be re-differentiated. An adult stem cell will be re-differentiated. Okay, actually this is how the dolly came. Okay, the cloning happened. What happens in the cloning? Okay, they took an ovum, and I will take my 46 chromosomes from my body, and I will keep my 46 chromosomes in an ovum. Okay, so an embryo requires 46 chromosomes, 23 from mother, 23 from father. Here what I did, I took a loophole. I took my 46 chromosomes and I kept in a ovum. Now ovum thought, okay, this is a fertilized egg, because now I saw 46 chromosomes. So what we did, we removed the ovary 23 chromosomes from the woman. I removed 23 chromosomes from the woman. Okay, I removed, it's an empty ovum. In this empty ovum, I kept 46 chromosomes. They are my own genes. And what happened, this this ovum become into an embryo, and that is called clone. Okay, that means this ovum has a microenvironment or cytokines. Those cytokines able to activate my 46 chromosomes, and chromosomes became into an adult. That means the trick is in the cytokines. The trick is in the activation of the genes. So he started his research. He started understanding what cytokines responsible for reverse engineering. What cytokines are responsible for reverse engineering. So what he did, he came to know that first he thought 22 candidates, 22 cytokine candidates. Then after research, he came to know we need only damn 4 cytokines. Take an adult stem cell, and keep this stem cell in these cytokines. These cytokines will switch on the genes, and this adult cell will be converted to an embryo or stem cell. It is one of the breathtaking discovery, students. I will show his research here. See, he took a skin cell. He kept some, he reprogrammed the skin cell with these 4 cytokines. They are OCT14, SOX2, CMYC, and K24. Okay. He took a skin cell. He reprogrammed the skin cell with these 4 cytokines. And what happened, it converted into a muscle cell. This is first time in the world, a skin cell was converted into a muscle cell without using an embryonic stem cell. This is an adult cell was converted into a pluripotent stem cell. Such a type of stem cells are called as induced pluripotent stem cells. We have induced pluripotency into an adult stem cell, leading to formation of induced pluripotent stem cell. You just imagine the potentials of induced pluripotent stem cell. That means hereafter I need not to rely on embryos. If I get a patient of Alzheimer patient, let me take my patient's skin cell, let me reprogram the skin cell into a stem cell. Okay, I took adult cell, I converted to stem cell. Now I will differentiate into a neural cell in the body, in the patient body. So what a beautiful thing. See, so we have understood the concept of molding the stem cells. So this is a first experiments where a skin cell was become into a heart cell. You can also see the cell beat here. See, this is the research of Shinya Anamaka. This is called as the induced pluripotent stem cells. Okay, so the idea is, let us take a biopsy. Okay, let us take the patient cell, let us reprogram. The reprogram stem cells are called induced pluripotent stem cells, and let us use these induced pluripotent stem cells for various purposes, for blood disorders, pancreatic disorders, neuronal disorders. Okay, skin disorders, even skeletal disorders can be addressed with these induced pluripotent stem cells. Okay, so this is called iPSC's. We took the patient's same adult cell and we injected stem cells into the patient. See? Yeah. Now, what is your thoughts on induced pluripotent stem cells? So this was done 20 years ago, almost 18 years ago. We already understood these stem cells. Why it didn't become a regular therapy? Is there any issues with the induced pluripotent stem cell? Yes, there are issues. There are issues with IPS. Okay, there are issues with the induced pluripotent stem cell. The issue is, see, already the patient is aged. Already he is 40 years old, and we are taking his a old cell and we convert it into a baby cell. Okay, listen, an old cell is highly prone to mutations. The chromosomes in these cells, chromosome has a something called telomere. The length of the telomere will determine the teenageness of a body. Why we are aging, why we are becoming old? Because the telomere length will be reduced. Chromosome, this is a chromosome, centromere chromosome. At the end of the chromosome, we have something called telomere. In a just born kid, the telomere will be 2 centimeters. But at 40 years, telomere will be, okay, just born 4 centimeters, 40 years, 2 centimeters. When you are dying, your telomere length will be very small, okay, 0.5 centimeters. That means telomeres will determine the age of a patient. If I want to know what is the age of patient, I will take his chromosomes and I will see the length of his telomeres and I will understand. Okay. Yeah. Now I was how I'm taking this induced pluripotent stem cell. I was taking already a partially aged cell, that is 2 centimeter telomere cell, and I was expecting it will live for next 40 years. It's not possible. So induced pluripotent stem cells will make mistakes. They have some mutations, and those cells won't be healthy. They are already old cells. So those cells looks like a baby cells. You can imagine a 70 years old person, but he looks like a 5 years old kid. Yeah, he appearance looks like a 5-year-old, but he is 70 years old. That is the problem with induced pluripotent stem cells. Okay. So, but the benefits are, there is no more ethical issues to use induced pluripotent stem cells. They are easy to obtain. Okay. No immune rejection. Disease modeling can be done. No toxicity can be happen. But the disadvantages of IPS are, reprogram is required. Reprogramming is not easy. It is very tough. There is a chance of activation of carcinogen genes. There is a chance of converting these induced pluripotent stem cells into cancer cells. These cells might convert into a cancer cells. We need to be very cautious. So that is one problem. Early lethality. These cells will age quickly. Okay, these cells will become old very quickly. That is early lethality. There is a high mutation rate. There is a less genetic instability. The cost is very high, and MHC downregulation can happen. MHC downregulation means autoimmune disorders might happen to these patients. So yes, still IPS, okay, sorry, induced pluripotent stem cells has a limitation. Okay, they have their own weak spot. Their weak spot is their age. Okay, so so far what we understood is the best way of getting stem cells is, ethically speaking, from umbilical cord. If the parents preserve their child's umbilical cord stem cells, that is the only safest, healthy, ethically right approach of treating patient diseases. Maybe in the future, or else we need a new research in the domain of xenotransplantation. Can I able to convert a rabbit or a dog or a monkey stem cells into a human stem cells? Can I able to reprogram other than human animals? Okay, other than humans, that means in the animals, can I able to make a human tissues? And the research is very it's in a very good progress. Recently, 2 years ago, I have seen we have genetically modified a pig with human genes, and that pig heart has been transplanted into a humans, and the human was survived. A human with a pig heart, that is possible. That is because of this stem cell reprogramming and re-engineering. But still the research is under development. And recently in 2021, we got a Nobel Prize in the gene engineering technology called CRISPR, cluster regularly interspaced short palindromic repeats. It's a genetic reprogramming tool. Okay, with this tool, there is a chances that in the future, the avatar might become a reality. If you see Avatar movie, they are making embryos in a tub. Okay, artificial water tubs have baby growing. Okay, Avatar will be grown. So yes, the research is in the direction of Avatar, and that is possible. Not in 10 years, but maybe within 50 to 70 years. Okay, maybe our child or our grandsons will see a synthetic humans. Okay, that is possible. So all of this is possible because of our understanding of stem cells. So stem cells can make avatar a reality. Thank you so much, students. This is about today, and we'll further sessions will discuss other aspects of stem cells. Any questions? Yes. If you have any questions, you can discuss. Yes, students. This is all about stem cells. Any questions? Am I audible, by the way?
Yes, you are, sir.
Yes, you're
Yes,
audible.
right. Any questions? If not, we'll
So I
wind up.
was just thinking, but I think I have the answer, because you said a person like that, the technique by Nayaka, he used an old person. Now I was thinking, why don't they use maybe like from when the person is a child? But I thought maybe when they take mesenchymal cells, it will be muscle cells. Then they don't know if that person is going to suffer maybe Alzheimer's, so they won't have to plant the neural cells. So I just thought maybe the answer would be like they won't know what you will suffer when you are old, so they cannot collect your cells when you're still young.
Exactly. We we cannot predict our future, right? But the best thing is let us prepare for it. Genetically modifying. Yes. See, these technologies also will be misused. People will work on stem cells for genetically reprogramming the cells. What if other class of scientists using these techniques to genetically program a sperm cell? What if this research is in a bad hands? They are making a designer babies. What if they're designing babies? Okay, so yes, there are some things, and we need a tight regulations in this research. Actually, if we are not tightly regulating it, uh, actually I will tell you in a nutshell. If Mahatma Gandhi was preserved, if Mahatma Gandhi donated his blood, I can make a new Mahatma Gandhi, right? Because I will collect his cells, the genes, I can make a clone of him. Say, just imagine we are bringing back Hitler again. Hitler has a unique fingerprint, right? Maybe there is a nuclear bomb where we need a Hitler's, fingerprint to authorize a nuclear bomb. And I made a clone of Hitler, and I activated the bomb. Maybe after 10 or 20 years, once he becoming matured. So yeah, that is an extreme level of bad usage of stem cells to cloning. So we need to be very cautious. We are not at all encouraging the embryonic stem cell research, not at all. We are only the government encouraging only for embryonic stems. The blood bank cord blood stem cells. Okay. Um, yeah, you just imagine if Stephen Hawking is alive today, we might resolve his issue. I hope you know who is Stephen Hawking. He's a scientist in a wheelchair. He has a neurological issue. So yeah, there is a future where even Stephen Hawking like scientist can stay healthy and alive because of these new technologies, the area in the research of stem cells. Yeah. So shall I end this lecture? I hope this generated enough curiosity into your minds. Okay. Please keep all these things in your mind and try to work on these issues. Okay. Parents, financial issues, relation issues, we can't escape from them. But try to have some passion always. Okay. A purpose of your life. And it is the curious questions like this, these topics will give a meaning to the life. Okay. It will have a sense of, the purpose of living. Yeah, at last we are a curious beings. We are a curiosity driven animals, humans. We love to explore new things and keep this exploration mindset always. Thank you so much, students. Thank you. I'm ending, and please fill the attendance sheet. Okay, I will float the attendance sheet and please fill it. Thank you so much.